talking about some recent results tracing high-Z galaxies and X-rays with JWST and Chandra, and potential insights that we can get from follow-up works with Axis. So these results are in the archive right now. They were accepted to AppJ, and a lot of collaborators here to acknowledge, especially a few in the room right now. So couldn't have done it without them. So to trace high-Z galaxies, or not even just in the high-Z regime, but at low and intermediate Z, we use the cosmic backgrounds. So the infrared, near-infrared background and the X-ray backgrounds, respectively. And so the near-infrared background is rather intuitive. It's the accumulation of near-infrared emission, mostly due to star-forming galaxies, stellar emission, but there are smaller components from black holes and other luminous phenomena in the universe. And so you can see in the plot on the right that if you calculate or if you directly measure the mean flux of the CIB in the near-infrared, there's an excess above what you'd expect from observed galaxy populations from galaxy counts, and that there's a kind of discrepancy in that there's an excess, and this excess we call the source subtracted CIB. And there are a few different explanations as to what this is, such as population 3 stars above a redshift of around 6, also intrahalo light, so gas and stars that are stripped from galaxy mergers. And so what we see here is that we need some way to study this excess and what redshifts it originates from, what are properties. And so I'll talk about what we use to study the CIB later on. So from the CIB, we can move to the CXB, which in the same sort of vein is the accumulated X-ray emission, mostly due to accreting black holes, and you have a hot gas component. And these accreting black holes are in the form of active galactic nuclei, and you also have X-ray emission from X-ray binaries, which trace star formation in their host galaxies, and you have hot gas. And so this is the cosmic X-ray background, and you see this peak at 20 to 30 keV, which I know almost everyone here knows. And we'll be focusing on the soft X-ray here, which has an unresolved component as well, which is thought to come from a combination of, again, AGN, star-forming galaxies, and hot gas, and potentially a population of high Z and heavily obscured AGN as well. So essentially now we have two different cosmic backgrounds with maybe the same sort of underlying populations, and we want to study them maybe together or separately, and so we can do that with the power spectrum. So using the angular power spectrum, you can study both the abundance and the clustering of these sources in the CIB and CXB, and you can study the cross power spectrum, which essentially tells you how what sources from one background might contribute to the other. And so the angular power spectrum is computed as follows. You have your fluctuation map. So you take out all the resolved sources in your IR and X-ray maps, and you compute the fluctuation map, and then you take the Fourier transform of that, and you get the power spectrum, which essentially tells you how much of your signal is coming from a particular spatial scale, with the frequency being Q. And you can do this sort of treatment here with the cross power spectrum, and you end up with this here. So you're taking the fluctuations in the IR and X-ray at a particular angular scale, and you cross-correlate them. So in this cross-correlation, we can define a coherence parameter. 1 and 2 just identify the different bands. So 1 could be X-ray, 2 could be infrared, or you can flip them. Doesn't matter. And so for 0, you have, for the 0 limit, you have no coherence. So none of the infrared sources will contribute to the X-ray background. They're fluctuations, and the one case tells you that the fluctuations from one background contribute fully to the other. And so what does this actually mean? There are two different extreme sort of scenarios. One being that the infrared background traces star formation and the X-ray background traces AGN, and the cross-power signal is essentially the clustering of these different populations in the same large-scale structures, occupying the same dark matter halos. And in the other extreme to the right, you can see that maybe they're not distinct populations that are just clustered together in the same large-scale structures, but rather you might have star-forming galaxies that are emitting both in the infrared and in the X-ray, or AGNs that emit in both. And intuitively, it would sort of make sense for it to just be a combination of both, as star formation can be traced both through the infrared and the X-ray, and AGN emit in the infrared. And so really the truth probably lies somewhere in the middle. And so how can we study this? And we do this in the Cosmos field. So we use the Cosmos Web Survey of deep infrared counts, and we focus our attention on the 277 and 4, the 2.7 and the 4.5 micron maps. And for the cosmic X-ray background, we use the unresolved fluctuation map produced from the Cosmos legacy data in the soft X-ray, again, 0.5 to 2 keV map. And so how do we compute these? Well, the Cosmos legacy CXB fluctuations have already been studied in other cross-power cases. And so we obtain those fluctuation maps directly. And so now we're just left to compute the CIB. And mind you, with JWST, if your Spitzer limiting flux, which is what was used to calculate previous the angular power spectrum of the CIB, it has a limiting magnitude, AB magnitude of 25, and we all know that JWST goes, 4 orders of magnitude below that. And so we essentially create or simulate almost the unresolved CIB with source counts from Cosmos Web. So here you take sources that are below this AB magnitude, or rather above AB magnitude of 25, and you place them onto an empty image of the sky. And from there, you compute the fluctuation maps as you would with unresolved maps of the CIB, and you cross-correlate them with the CXB with the treatment that I shared before. And so I will show you here that we do this for 3 different redshift intervals, 0 to 3, 3 to 6, and 6 to 13. And to show you how this sort of looks, here's a GIF of the accumulated light. So you first start off with 6 to 13, the sources from 6 to 13, and you move to 0 to 3. And you see that it starts off with all the different sources, and then at the end, this is the fluctuation map. And so, as I shared before, the CIB is just the accumulation of all this light, and here's the fluctuation map showing just that. And you might see some kind of like circles and squares. Those are just masked out features from Cosmos Web. So here are some results. So we see here a few different interesting things. One is that this unresolved excess in the CIB cannot be attributed to these JWST sources, which does make sense here because our results are consistent with CIB reconstruction attempts that are in pretty similar agreement if you see in the bottom left, HRK12 being the CIB reconstruction. But regardless, even though it doesn't match up to this unresolved excess component, you still have a shot noise component, which is your random kind of white noise term, and you have a clustering term at each redshift interval. And further on, we have a statistically significant detection of X-rays, and they're both around 5 sigma for both 2.7 and 4.5 micron maps, and they're even higher actually at high Z. And so in the bottom row, this is for the 4.5 micron band. Although you see a similar sort of thing in the 2.7. And so you see a statistically significant cross-power signal at z greater than 6, which there are a lot of interesting things that we can do with this, and I'll share some of those now. And it's interesting to note that even though our CIB auto power spectrum can't recreate this unresolved excess, the cross-power signal with the X-ray still puts you with previous measurements of the unresolved CIB and CXB. And so what this tells you here is that even though it doesn't match up to that excess, you still have the underlying sources that are contributing to this cross-power signal are still there from these galaxy populations with JWST. So I'll speed up a bit. So from these maps, we can compute the galaxy biasing, the purple being the infrared, the Cosmos Webb sources, and the green lines being estimates from the X-ray. And they're kind of what you would expect. They're a bit higher than the star-forming galaxies traced by Cosmos Webb. And the high Z is consistent with effective bias measurements from Ricarta et al. That studied the different seeding scenarios contributing to the X-ray background. And we can also estimate the flux production, which is within the upper limit from Capelluti et al. 2017. And we are within 2 sigma of resolving the extragalactic soft CXB. So with these flux production rates, we can take a look at what we can do with AXIS. So if we just assume a Euclidean power law for these sources at redshift greater than 6, and if we take this kind of characteristic flux to be of the moderately deep axis fields, you can get a cumulative source count that is, you can see it's not too far off from what you expect from high Z seeds from Ricarta. And so they're not too far off. They're a bit lower, but again, we assume a Euclidean power law, which especially high Z, it's not really tested. And so with AXIS, we'd be able to probe these sources. And not only that, but with the CXB maps that would be created with AXIS, you could actually chop down your sources at different X-ray fluxes and cross-correlate those flux-limited maps with your JWST maps, and that could actually provide some insight as to what sources in the X-ray are boosting your cross-power signal with JWST, as you'd expect star-forming galaxies to maybe dominate the faint end, and so you can actually sort of determine what your characteristic populations are with AXIS. So thank you, and I'd be happy to take any questions.
Any questions?
Very nice talk. So I'm a little confused. So want some clarification. So all the sources that JWST is seeing at redshift greater than 6, even when you account for them, the cross power excess still persists. You need something more. Is that the conclusion? Or are you accounting for?
No. So this excess that I was referring to was in the infrared,
Right.
not the cross power signal. I didn't mean to.
You want to show the plot again?
Yeah.
I think I missed the.
You mean this one?
Yeah.
Yeah. So the new results from Kashlinsky et al. Have in the purple and the orange aren't accounted for by the JWST sources, but the cross power spectrum can be recovered with just these known galaxy populations. Yeah.
Okay.
Anything else? Quick question. All right.
Thanks for your talk. Just a really quick sort of naive question. Towards the beginning, you mentioned that the CXB could have like a stellar component to it. So at pretty high redshift before the peak of the maximum star formation rate, how much do stars contribute to that budget? Are there any estimates?
I think I don't know the exact percentage, but I know it's relatively low. I mean, it's definitely subdominant. Yeah.
Okay, while our next speaker comes up, let's thank Aidan again. Thanks. PowerPoint version.
Yeah, it's the Google Slides.
Yeah. Hopefully this one. Cool. Great. Our next speaker is Yash Gursahani. Take it away.
Okay. All right. Hi, everyone. I'm Yash Gursahani. I'm a second-year grad student at the University of Maryland, College Park. I've been doing some work with Chris for the last year and a half or so now, and I'm excited to tell you all a little bit about it today. So we've been studying obscured AGN and their X-ray properties at high redshift. So when I say high redshift, I mean, redshift 8 and above, redshift 10, something like that. So we know that there's a local bias toward unobscured AGN. Let's see, can I play this? No. Sorry, I think this was supposed to play automatically, but it didn't. Anyway, I can describe it for you. So this is supposed to be an animation from Claudio Ricci, and what it shows is that as you crank up the column density, you basically lose the soft X-ray flux. And eventually you're just dominated by this distant reflection component, and that's due to photoelectric absorption, mainly in the soft X-rays. So we're biased towards unobscured AGN because of this effect in the local universe. And there's a special designation of Compton-thick AGN where the column density is roughly 10 to the 24 per centimeter squared or greater. So what about high redshift here? So you've seen this already. These figures, so UHC1 and GHC9 have been detected at redshift 10. And the important thing to note here is that at redshift 10, the X-rays that we are observing are in the rest frame at much higher energies. So for UHC1 on the left, it's roughly 22 to 79 keV rest frame, and for GHC9, it's 5 to 30 keV, at least the counts that have been observed. So we want to think a little bit more about what changes when we're up at high redshift and at these harder X-rays. So two of these changes, number one is, so there are two main changes. First is that there are harder X-rays at high redshift, and two effects of this. One is a smaller Klein-Nishina cross-section for Compton scattering. So that means if you have some obscuring medium surrounding your black hole, there will be, on average, less scattering back and forth in this medium, and more photons will get out. We expect that to happen. Now, this is a moderate effect, but the second one is a little bit more important. When you go up to harder X-rays, the scattering is forward peaked. So that's what the plot is showing on the right here. So these are sort of probability contours, more or less, in polar space. So as you go up in energy, the photons are more likely to continue in their initial direction that they were moving. So if they're isotropically emitted from a source at the origin, they should continue to move outwards on average. So more photons, again, will get through rather than scattered around and eventually absorbed. Another important change with high redshift is lower metallicity. And what this will do is it'll give you a lower optical depth. It'll give you less interactions with, say, iron. Iron is an important element that we consider. And while we're on the topic of iron, at high redshift, you also have the effect of less type 1a supernovae having gone off. And that's something that we're starting to look into now. But because of that effect, the iron opacity will be decreased. It'll be a smaller effect at high redshift. So again, you get this effect that you expect more hard X-rays to get through rather than get absorbed. So the guiding questions for our work is, what are the properties of Compton-thick AGN at high redshift, so these very obscured objects, and could we potentially observe them? So now I'll talk about a little bit about the methods that we used. So I wrote a Monte Carlo code. This is similar in style to other codes that are out there, but it uses this geometry that you see on the left. So just want to make it clear, there's no accretion disk here. We're only probing the distant neutral reflection. I include 11 different species other than hydrogen, and 10 viewing angles. So sort of, edge on, face on, and in between. And then I have a power loss source that's the number of electrons per energy bin proportional to e to the minus gamma. So that gamma is something I can adjust as I please. And it's between 0.2 to 200 keV. Another very important, let's see, I don't know if that works very well, but the opening angle of the torus is going to be very important as well. So keep that in mind for future plots. So these are the interactions I include. Again, relatively simplistic code, but there are lots of different things that you can do when you change these parameters. So one thing that can happen is nothing. So the photon can just pass through basically undeterred through the medium. If it interacts with hydrogen, you can get Compton downscattering. So there will be no upscattering here because I'm just considering a cold neutral medium. You can also get fluorescent line emission from the other elements. That line photon can go on to kick out an electron, which then means you lose the incident photon. So either the fluorescent line photon escapes or it gets absorbed. So this is the parameter space that I explore. So I have a wide range of column densities, a few different opening angles, and a few different metallicities, all in solar ratios for now. That may change in the future. And I also have a zero metallicity, set of runs that I did just to check against. Okay, so now I'll talk a little bit about the spectra and the simulated observations, especially with AXIS. So this is a lot, so don't focus on every panel here. I'll zoom in on a couple in just a minute. But the key here is I have a set of metallicities going left to right. I have a set of column densities going from top to bottom. And then the orange spectra will be the edge-on, and the blue will be the face-on. And then I do this for two different geometries. So the more open torus, which is the 120 degree, and then the closed up one for 30 degrees. So I'm just going to focus on this bottom row really quickly so we can see the difference in geometry. So if we just look at the face-on viewing angle for these spectra, in the 120 degree case, the face-on angle can only gain photons. So you have direct emission that's going up to the observer, but then photons can also scatter off this torus and also be directed up towards the observer. But in the 30 degree case, even the face-on viewing angle, quote unquote face-on, is being partially covered. So you can lose photons from absorption or scattering, especially at soft energies. So it's sort of similar for the edge-on. Of course, when you're looking edge-on, the photons can be lost out of the line of sight by scattering, and they could be absorbed. But the interesting case here is that when you close the torus up more, you get the Compton hump, and the line emission is boosted. And this is just the effect that less photons are lost when you close the geometry up. So less of the direct emission is actually escaping right away, and more of the flux can come out on the edges. So here, actually, if I go back, the Compton hump is just a few, it's a factor of a few below the black dashed line, which is the continuum that I put in. And so, that may make you think that the Compton hump could be a viable source of photons that we could observe from these very obscured objects. So then I went ahead and did some spectral simulations. So Chandra versus AXIS. So very important distinction to make in all of these is that, so AXIS is in blue, Chandra is in orange. And the important thing here is that I don't include a background for Chandra. So it's 7 megaseconds, which is the Chandra Deep Field South exposure. And so 7 megaseconds, no background, whereas for AXIS, I include the background, which is plotted in gray. So the top row has the bright 10 to the 44 erg per second X-ray luminosity. The bottom row has 10 to the 43 erg per second. And so you see here that metallicity has a moderate effect at soft X-rays. So metallicity is lower on the left, higher on the right. But
really it's the brightness that counts. So the top row is much more observable. The bottom row axis could see. Chandra has a hard time keeping up. Here I keep the column density at 10 to the 24 per centimeter squared, but if I crank it up 10 to the 25, axis even becomes quickly background dominated. Whereas Chandra really has no hope at the more dim luminosities, whereas Axis could still see the 10 to the 44 erg per second, even when they're very obscured. So this says, Axis could see these bright, heavily obscured AGN, even some of the dimmer ones out to redshift 10. Chandra cannot keep up, at least in in this case. Okay, so I'll just quickly move to my conclusions. So the main takeaways, so the Compton hump could provide a source of observable photons for Compton thick AGN. See, high redshift sources do give us the best chance just physically for photons in our usual observable band to escape, and this is better for lower metallicity. Of course, this depends on the details of how bright they are, what is the actual power law index, how many photons you have in some energy band, etc. And lastly, Axis could conceivably see, as we've heard already today, these Compton thick AGN down to X-ray luminosities of 10 to the 43 erg per second at redshift 10. So I will stop there, but I will warn you, if you ask me any hard questions, this will be my reaction. So thank you.
Great. Does anyone have any hard questions? There you go.
Very nice work, Yash. I really like the fact that you did the simple Monte Carlo that is agnostic of what the accretion disk or how this torus is forming or whatever, which is great. I was very curious. I think to make bolster the case even more for Axis, you could just add, even though the areas are small behind lensing, getting a luminosity boost from magnification from lensing. Just go for it, right? And make that plot. It'll look very good for Axis. Yeah.
Yeah, this is something that Chris and I had spoken about briefly. So for like the UHC1, I think it's a magnification of 3 point something.
Take their magnification profile, get the boosted luminosity, and use that plot.
Yeah. Right. Thank you. Yeah.
So I'm curious, are there any kind of low redshift analogs, dwarf galaxies, other things that we could search for where we have, much higher sensitivity to just see if we see signatures similar to this in what we know are low metallicity systems, or is it the metallicities at low redshift are just still too high to really study these types of obscured AGN?
That's a good question. So I've been talking a little bit with Richard about this and some others, thinking about the local universe. Now for the truth of the matter is here we're considering metallicities that are in number one in solar ratios, which we don't know if that's 100% true at high redshift. So that's one major difference. The other difference is that the metallicities considered here, are they realistic even at high redshift? We don't know for sure. I think at low redshift we know that these dwarfs have these low metallicities. We can measure them pretty well. So that would be an interesting thing to try for sure. Yeah.
Great, thanks. Any other, Ryan, did you have one? Yeah, go ahead.
Thanks for this really nice work. I'm curious, we have evidence from a range of different avenues that some of the obscuration and also some of the X-ray reflection comes from scales well outside the torus. And so I'm wondering, is there a straightforward way to analogize this modeling of the torus to things that are, hundreds of parsecs or kiloparsec scales, or could you use a similar approach to do that, but just with a different geometry?
Yeah, so the nice thing about this particular model is as soon as you specify the geometry, the problem becomes roughly scale free. So what I put in is the column density, and the code, it knows what the physical scale is, so it just adjusts the number density in the medium to do this. So if I adjust that scale to be much larger, and you could also imagine including multiple, having this torus and having some shell outside that has something else. And that could be done fairly in a straightforward way. So yeah.
Okay, thanks. We should move on, but let's thank Yash again and. Version. PowerPoint or PDF?
Well, I think PDF is better.
PDF, okay. Right. So our next speaker is Alessandro Peca, talking about AGN across cosmic time.
All right, thank you. Hi, everybody. I'm a postdoc at Eureka Scientific, working with my Koss. I'm also laboratory associate at Yale University, and it's survey time. So let's talk about what AXIS can do about heavily obscured AGN across different redshifts. So very briefly, a lot of people before me already spoke about this. Why do we care about obscured AGNs? Well, we have several reasons. For example, here you can see one of the many examples of the X-ray background. We can reproduce this X-ray background using different populations with different level of obscuration in AGN. And in particular, you can see here the orange one and the red ones are the contribution from the most obscured AGN populations. So this is why obscured AGN are important, but also they are important where we are talking about AGN and galaxy evolution and coevolution. We know from several theoretical and empirical models that obscured AGNs are in a very, very key phase of the coevolution. They are caught in a phase in which there is this radiation pressure that is going to clear out all the obscuring material, and then there can be a lot of interaction with the Ox galaxy, interaction like quenching star formation, and so on and so forth. And also, if we extrapolate all of this at very high redshift, as Priya was mentioning this morning, this is also very important when we talk about primordial black hole seeds. And several other reasons, like everybody's talking about X-ray weakness. So obscuration can be one of the possibilities to explain this peculiar behavior on JWST sources. However, heavily obscured AGNs are just very difficult to find. And the reason is because they are extremely, extremely faint. And this is also why many people are working on this topic. So as an example, this is a work by Tonim and Anna in 2019. This is the NH distribution in the local redshift, so local universe, so low redshift universe. And you can see that, especially in the Compton-Tick level, so NH is larger than 10 to the 24. Here you can see different values from different works. You can see that the uncertainty is huge. So we need to do better for this class of AGNs. And again, if we try to trace, so that work was in the local universe, if we try to trace the obscured fraction of Compton-Tick sources up to high redshift, you can see that we get discrepancies that are almost as large as the entire plots. If we lower down the NH, so if we talk about more generally about obscured AGNs, so NH is larger than 10 to the 22, there is more consensus in the community. So we know that obscuration increases with redshift. And this comes from several X-ray surveys. I just mentioned some of them here, but there is also indication from infrared studies. And just as a reminder, the host galaxy makes a huge contribution. So as you can see from this work from Gilles et al. 2022, looking at the molecular gas with ALMA, they show that the NH coming from the host galaxy at high redshift can be up to the Compton-Tick level. So this is something that we also need to consider when we study obscuration in AGNs. So what can AXIS do in all of that? I took this slides from Nico's paper. As you can see, compared to the yellow region here, which shows the current coverage in the flux area plane of the current X-ray surface, axis will do great. So we are going to push down the sensitivity limits, and this is going to be great for obscured AGNs, which are indeed very, very faint. And what I'm showing you here, so this is for axis intermediate survey. On the left, you see Compton thin objects, so log NH is larger than 10 to 22. On the right, you see Compton thick objects color-coded by different luminosity bins. What I did, I just took simulations provided by the Axis team. I think they are made by Stefano, which is here in the room, and you can see how well we can do. So we can push the detection of heavily obscure sources up to redshift 6 or so, in this case for high luminosity objects. But if we take the Axis deep survey, we start seeing also the lower luminosity object, and we can easily study this obscured AGNs population up to redshift 4 or 5, and for specific luminosity population, we can even reach higher redshifts. But how this can be related to the local universe? So we are now in the JWST era, and JWST very high redshift sources are just unmatched by current X-ray observatories. We just cannot do it. We have some examples, but if we are talking about population studies, we cannot do it. So our idea was, let's try to find some local analogs to try to understand better how these objects work. So we went into the BUS survey, which is this spectroscopic survey in which X-ray detections, X-ray data come from the Swift-BUT telescope. So very high energies from 14 to almost 200 keV, meaning that we are almost unbiased again obscuration. So we can study very well obscured sources. And we took this high luminosity regime. And the reason is, again, high luminosity AGNs are extremely important in black hole evolution. And we selected this pretty unique area of this low redshift NH luminosity plane. We selected 21 Seyfert 1.9 and Seyfert 2 sources at high X-ray luminosities, for which we have very high signal to noise ratio. And we were able to make a spectral analysis on a very broad band. So we have soft coverage, XMM, Chandra, and Suzaku, plus for all the objects we have Nustar, so we can extend the analysis to higher energies. And now I'm just showing you a couple of results. So I think this is interesting. So here you see the Eddington ratio versus NH plot, color-coded by luminosity. And you see that the gray area is the so-called forbidden region. Why forbidden? Because at high Eddington, you are supposed to have this huge radiation pressure that is supposed to blow away the obscuring material. However, in our sample, we have half of the sources in this region. So this is important because it's telling us that these sources are caught in the moment in which this particular K phase of AGN evolution is happening. And this is also important because in these specific sources, you expect to see transitional features, for example, winds or outflows. But guess what? If you go into the archive today, this guy over here, which is at the very edge of the forbidden region, we found an ultra-fast inflow, which I think is extremely interesting. We don't have so many inflows in the literature. And so please, now I don't have the time to go into the details, but please go check the paper and ask me questions if you have any. But this is also a signature on how many things we can do with X-rays. This is another result. So this is optical spectroscopy. So we just took our very high signal to noise optical spectra in the sample. We stacked them together, and the result is this blue spectrum here. And then we compared with the red spectrum, which comes from JWST, high redshift, narrow line agents. So the JWST spectrum is from the Cheers survey, is from the work from Mastolari et al. 24, and we're talking about narrow line AGNs between redshift 2 and 9. And there are, I mean, in the full spectrum, there are some differences, but the major difference is zoomed in here. We have this strong neon 5 emission line, which is completely lacking in the JWST spectrum. Why this is important? This is important because to get neon 5, you need a ionization potential, which is that needs to be larger than 97 EV, which means that when you see neon 5, you have an AGN. Also, neon 5, this is another work that has been submitted by the BUS team. If you check, there is neon 5 doesn't care. Neon 5 doesn't care about X-ray obscuration. So why are we not seeing neon 5 in high redshift AGNs? We actually don't know. We have some ideas. For example, we are assuming that local AGNs are behaving in the same way that high redshift AGNs, which may come with caveats. There may be also metallicity at play. Also, it would be strange because if you check the other emission lines, we don't see so much differences. I strongly believe that is the ISM that is playing a role here. As I showed you before, at very high redshift, the ISM matters. So even if we study AGNs, we should keep in mind that there is a NOS galaxy there, and I'm happy to take any question even during the meeting about this topic. So again, why studying local analogs is important? Again, local objects, broadband spectroscopy, very high signal to noise ratio, very nice modeling. We can use this modeling to make templates, very precise templates, to see how obscured AGN can look like at high redshift. And this is what we did. We took some of our best study source, and we artificially reshifted it to higher redshift, and we simulated how this source will look like with axis. And very briefly, here you can see the shaded gray are the results from our spectroscopy, which you can consider like the gold standard in terms of error bars. And you can see that axis with exposures which are around or below 100 kiloseconds can improve these studies up to redshift 1, more or less. But if you take the axis intermediate and deep surveys, we can expand this kind of studies up to redshift 5 or even 6. And these are my summary and conclusions, and I'm happy to take any questions. Thank you.
So I'm going to ask you to speculate a little bit about the difference in the neon 5 emission, because I find that fascinating.
Okay, thank you. Well, if I may add something, there are detections of neon 5 in JWST spectra. So it's not that it's not like we don't see it anywhere. However, when you stack the signal, the majority of the sources do not have it. So that's something that I should clarify. Yeah, but yeah, thank you.
Yeah, I was just going to comment. The interesting thing is they're matched in O3. So you stack and you match in O3. That should, fix some of the issues with metallicity and the other thing.
Wasn't what I was thinking about.
Yeah.
What I was thinking about is this. It's a much higher ionization line.
Mhm.
And so that hints at real physical differences.
Yeah.
But these are all BPT selected, which is hard to do at high redshift. They think they're doing it, correctly. So there's some,
I understand.
add one more piece to the answer. Alessandro has done all the hard work. And there are two other bat-related papers on neon 5. The blue line, which Alessandro's talked about, and the IR line. And for both samples, the rate of detection in the low redshift universe of neon 5 is 70%. And both papers have looked for correlations about why, and the signal to noise is high. It has not yet been figured out that there doesn't seem to be a difference in the Eddington ratio, black hole mass, luminosity, or whatever, that distinguishes the 70% detected from the 30% non-detected. And so the only thing that we've left that we have to understand is it could be obviously the SED that's different. But why the high redshift universe has this average that's much less than the low redshift universe, maybe it's the SED, but that hasn't been studied well yet.
Okay, thanks. Any final questions? If not, let's thank Alessandro again. Okay, and our next speaker is Joanna Piotrowska, who will tell us about constraining supermassive black hole growth.
Thanks a lot. Right. So, in the spirit of talking about black hole growth and spin, I think I don't need to convince anyone in this room that cosmological growth of supermassive black holes is critical for understanding how the universe evolves, as has been beautifully argued by Priya earlier today. And I myself have a vested interest in this because, as we all know, supermassive black holes are critical to the evolution of their galactic hosts, and there is no way you can learn much about feedback if you don't know the energetics about it, and hence how exactly it's fed across cosmic time. And of course, as has been shown in previous slides as well, it's not only about how black holes grow, but also how they came to be. And both of these can be answered potentially by looking at how black holes grow as a function of time. Now, black holes themselves are absolutely wonderful physical systems that only have 3 parameters: mass, charge we don't care about, and of course, angular momentum. Because mass cannot tell you how mass grew as a function of time, you're basically left with one other parameter that can hopefully tell you something about its historical growth. And for the rest of the talk, I will assume the spin values, the spin ranges between 0 and 1 in its absolute values. Now, one thing we haven't talked about yet today is how we measure spin in real observations, and that's important to list here so that we remember all caveats associated with it. We've got black holes, geometrically thin and optically thick accretion disks, razor thin and flat, some form of a corona that is a source of X-ray emission that comes from upscattering of thermal photons from the disk. Part of that emission, of course, will be emitted towards the disk, reprocessed or reflected, and comes back to the observer. Now, how you make the measurement? Well, what you get out of this reflected emission is the iron line complex. That would be the first peak in energy, followed by the Compton hump. And for a black hole that's non-rotating, that looks roughly like this. Now, the way we can actually constrain how much angular momentum a given black hole has is by looking at the gravitational distortion of the iron line complex. As those photons try to get out of progressively deeper gravitational potential wells, they get redshifted, and that's illustrated on the right-hand side with this very faint background. So that's the name of the game, and you're effectively trying to differentiate between the top and the bottom on a continuous scale between 0 and 1, and that's the state of the art you get, roughly less than 50 or so measurements. Now, the first thing that should strike you here with all the authors listed here across time is that A, these do not come from homogeneous surveys designed to search for these signals. They come from different authors spanning multiple different methodologies, statistical methods, and approaches. And on top of that, over half of these measurements are only lower limits as opposed to constraints with meaningful uncertainties. Now, Coming back to why black hole spins matter, well, as we've heard from Angela earlier today, you can black hole spin and growth are intimately connected. If you think of ordered accretion through aligned accretion disks, black holes will on average spin up. If your accreting material has randomly distributed angular momenta, on average, it gets to spin down. And when you've got supermassive black hole mergers, depending on the relative orientation of the progenitors, you can get either spin up or spin down, depending on the initial conditions. Now, this has shown to have profound effect on the redshift zero distributions of spin parameter in semi-analytic models. But more recently, people have started implementing that in full hydrodynamical cosmological simulations that include star formation, supernova feedback, and AGN feedback. So that is, of course, in contrast to what Angela has been talking about earlier. We are not populating dark matter merger trees. Instead, your universe is evolved with full hydrodynamics and dark matter plus all the extra subgrid physics. So the main result that Ricarda and Rebecca have shown in their paper back in 2023 is that if you look at the Horizon AGN cosmological simulation, and I'll switch the slide right now, those black holes that grew only via accretion, that's the blue population in the slide, tend to have spin parameter values concentrated at close to 1. Now, if those black holes have grown via both accretion and mergers, their spin distributions would be different. So if you take that, that simulation and then project the one-dimensional histogram on the left onto two-dimensional space as a function of mass, spin parameter on the y-axis, account for the bias, well, the relationship between radiative efficiency and spin for Novikov-Thorne disk solutions, you get two populations of black holes in that spin mass parameter plane. Orange, those that grew via accretion mergers, and accretion only, the blue in the top, very thin population. And even by eye, you can tell that they're statistically different. However, they're not statistically different enough when compared to current constraints. And you can squeeze some simple statistics out of it, say binning your parameter space by mass to only get lower limits that are not exactly constraining. And that's where things get interesting for this talk, for this conference, right? Because that's a perfect opportunity window for future X-ray missions to improve on what we currently have. And I should have said that before, but I think it's important to highlight that the constraints I'm showing you right now in the slide, they took approximately 2 decades of observations and countless PhD lifetimes and dollars to compile. So the exercise I'm going to show you in a second treated as a proof of concept study where we start with a known distribution of sources in the universe is taken from the BAS survey. There is a very good reason for this. The BAS sources match Horizon AGN in mass distribution rather well. And what you're going to see in the slide right now is a simulation of what observing 100 such sources would give you by drawing masses from known mass distribution in the BAS survey, assuming a random draw from spins from the Horizon AGN cosmological simulation for given supermassive black hole growth scenario, accounting for spin measurement uncertainty, this time simulated for broadband reflection spectra. And that's the outcome you would get from such 100 observations is presented on the slide. Orange points for accretion and mergers, blue points for accretion only. Then you can do your favorite averaging in bins of black hole mass and realize that these two populations are now statistically separable and strikingly different. You repeat that 1 million times for different realizations of uncertainty, and you get a median universe expectation as drawn from Horizon AGN of that in the slide, compared with current constraints. Not too shabby. Now, the thing we're doing right now, and is arguably even more exciting, is understanding how the orange and blue points will look in the axis space. And one thing we have to worry about right now is what are we going to do if we lose the Compton hump above 10 keV? So one of the things that one of the problems that the community has converged on recently is the potential problem of degeneracies between, say, wind models and X-ray reflection spectroscopy for AGN, which renders it near impossible to constrain spin parameter with soft X-ray measurements only. However, AXIS gives us an extra dimension. So not only can we go to higher redshifts to study these two populations as a function of time, but also hopefully we can take advantage of the Compton hump moving into our observational window to break those degeneracies. So what we're doing right now is effectively looking into all of those things I've just mentioned. And long story short, if you've done those simulations already and have insights or would like to talk more about different predictions from models, because that's incredibly important, let's talk. We've got 3 days to do this, so let's join forces on this one. Now, as a final note, I also wanted to say that spin parameter measurements are not only means of they don't only serve as that diagnostic for what black holes could have done, assuming a physical model. If we get enough population spin measurements with the current direction the simulations are going, we might end up delivering tight enough constraints for calibrating subgrid models for cosmological simulations. I know it's a big ask, and I'm probably thinking 10 years in advance for the models, but in principle, that would be one extra dimension for calibrating our subgrid physics if we want to include spin evolution on the fly. So on that note, I'd like to leave you with my conclusions. The main takeaway point here, well, there are 2 main takeaway points from my talk, really. One is that currently available constraints are simply not good enough to make meaningful inferences about how black holes grew as a function of time if we're looking at redshift 0 X-ray reflection spectroscopic measurements for spin. Now, there is a chance for opening that window with new observatories, and hopefully AXIS is one of them. So it would be wonderful to make a strong case for it. Thank you.
Lots of hands.
Thanks for a very, very interesting talk. I was very curious, how are you separating the population in a cosmological simulation of growth by accretion versus growth by mergers? Is it a threshold of the final mass that is assembled? Okay, what is that number?
10%. So accretion only is no more than 10% growth in mergers.
I see. And then I was curious about the BAS survey. So there's a mass function match. Is there a luminosity match as well or not?
Oh, that's an excellent question. And I don't know the answer off the top of my head. I would imagine not.
So I think that's kind of important.
I agree. Yes. I agree. It completely is. That's why I asked you for kindness in treating it as a proof of concept.
It's very interesting, though. But yeah.
Horizon AGN predictions.
AGN, the simulation. Yeah. So. The low redshift, right?
The low
He's
redshift,
showing here. The other question is, when you are showing the plots with the spin measurements, they are over a range of redshifts, right? So when you're overplotting the simulations, are you looking at the same bins? Like how are you doing the comparison? Yeah.
These ones you mean? Yeah. Well, in practice, most of these sources do not reach very high redshifts, right?
Right? One or less.
No, less than that. One. So that's 2 out of 50. Yeah.
Massive point there.
Right. I agree. Yes. So for all intents and purposes, what you're looking at is redshift 0 snapshots of all the simulations, apart from New Horizon, which unfortunately goes to 0.25. So we can't do better than that. The simulation has stopped there.
Okay. Thank you.
Just one very quick, I would amplify your point about redshifting of features into the axis band. Also, the ion line redshifts in, and as you go to higher and higher redshifts, it just goes to the more and more sensitive parts of the detector. You know, so our 6 keV effective area versus our 2 keV versus our 1 keV, it just gets better and better as you go to lower energies. And so as you go to higher redshifts, your ability to constrain spin does not fall off as fast as you might think just from the fact you're going to fainter sources.
Yes, and that actually touches the one thing I've been thinking about all the sessions since I've talked to Richard before is how many counts exactly we need in order to make a meaningful spin constraint. And order of 1,000 that has been quoted. I'm not sure that's good enough for the uncertainties. 1,000. No. No. For the spin constraints we want to get here, these are clearly numbers out of question. So now the name of the game is really how much time do we need to pump in these individual sources to make that meaningful.
Yeah, you showed that nice those nice simulations from the Horizon AGN simulations. Could you just comment briefly? What is the level of uncertainty in the spin distribution predicted, considering the treatment of the subgrid accretion physics as well as the treatment of the mergers, both of which are, of course, very challenging?
Absolutely. So that's the one thing I had to skip in favor of time. Horizon AGN. Key points here. It's an Eddington limited Bondi-Hoyle-Littleton type accretion prescription for how quickly black holes accrete. That's first. Second for spin evolution. When it comes to mergers, these are effectively fits to suites of numerical relativity simulations by Rezzolla from 2008. If you're familiar with that compilation, so that's for the mergers. As for accretion, there is necessary stochasticity involved because as those black hole particles swallow up mass from the result hydrodynamical grid, your say the uncertainty of your incoherence of your accretion will be simply large because of how stochastic that is. So I'm afraid the distributions themselves are not very certain, and I wouldn't, and I don't think anyone in the Horizon AGN collaboration trust those as face value results. That's why they came up with New Horizon, where they treat spin parameter evolution on the fly in higher resolution and includes spin down via jets, which seems to be important for their most massive black holes, which is not included in that model.
We do need to move on, but as Joanna says, we have 3 days for questions, so I encourage you to.
Maybe that's an important comment.
A quick comment.
It doesn't work at higher redshift.
All right, let's thank the speaker again. And our next speaker is Mike Koss. We'll talk about probably dual AGN. Yep, I was right. All right, go ahead, Mike.
Okay, great. So it's great. We're kind of switching topics. So it's great, Joanna talked a little bit more about mergers. So I want to talk to you about a potential survey that we can do with AXIS that I think will really revolutionize our understanding of black hole growth in merging galaxies. So why do we care about mergers? Why do we care about dual AGN? Because we're really looking at this rich story over 1 billion years that most galaxies will have these major mergers. And in that phase, they'll have black hole growth through accretion from gas. We think that there will be a dual AGN phase. We think there will be more obscuration, and that'll lead directly into binary AGN, gravitational wave emission, and then some very interesting, unique sources from black hole recoils, or if we have stalled black holes and a third one comes in, we'll actually get a black hole that gets kicked out via gravitational slingshot. So for the PI-led survey with AXIS is really going to do this across cosmic time because of the very stable PSF across the full field of view. So there will be 20,000 AGN where we can do a dual AGN study. And I'm just going to talk a little bit more about the figure on the right. So if you look at those, I know there's some people online, so if you look at the purple and green, that is actually simulations from Horizon and Astrid for merger-driven accretion causing dual AGN, and those are the fractions, so you know 1 to 4%. Red is the only secular accretion, nothing from mergers, and those black crosses are what if we believe the simulations, what we would get from AXIS. And then the brown at low redshift is from a study I did a while ago using Chandra to survey 170 AGN and look at the ones that are mergers and look at their dual AGN fraction. So it was not a large enough sample, so it had fairly large error bars. But what you'll notice is even with the error bars, the fraction was significantly above what we expect, either from secular accretion or from predictions from simulations. The other interesting point is at redshift 3, there's a study that looked at the Chandra deep field that didn't find any dual AGN, suggesting it might be lower. Another interesting, more recent study was suggesting that the dual AGN fraction from JWST from Perna was 20 to 30% at redshift 2 to 6. So there's just a lot of interesting conflicts that we're trying to resolve right now to understand how important dual AGN are and how important mergers are. And one more explanation of how powerful AXIS is for doing these distant dual AGN surveys is to show you Chandra versus AXIS at redshift 3. And the real power of AXIS is because you get this 1.5 arc second across basically the full field of view, you can survey 70 times faster with AXIS because you get your effective area plus the much larger field of view. So this is showing Chandra versus AXIS at different off-axis angles within the field of view. So as you go 3 arc minutes off or 5 arc minutes off or 7.5 arc minutes, and you can see you really can't see the dual AGN in Chandra. And when you look at AXIS, you have 150 counts and you can clearly see the two sources. So it's really powerful to do this across redshifts. But there's a big advantage to studying nearby galaxies. So this is NGC 6240 shown in HST on the left, and then in the near infrared with adaptive optics imaging. And you can see just the rich complexity. So the two sources in the center are the dual AGN. You can see the rich complexity that you see from the dust, all the way across the galaxy. This system has strong feedback. You can look at the gas. You can look at the black hole properties, precisely measuring the black holes, looking at the dynamics. You can look at jets and other features. And because these sources are so nearby, and we're going to have Euclid imaging covering the sky and Roman imaging in the near infrared covering the sky. We're going to have these incredibly rich images of nearby galaxies to perform these very detailed studies to understand what types of mergers grow black holes. This is from my study from a while ago. So it's 10% in the sense of there's some lower luminosity duals that weren't in the previous slide where I showed basically 5%. And you can see some of the, just looking at SDSS quality images, you can see many of these sources have very different morphologies. Some of them are major mergers, some of them minor mergers, some of them are groups. So there's a lot of complexity and richness in what actually grows a black hole. So the type of survey that I'm suggesting with AXIS, because we have this large increase in effective area, we could actually do a dual AGN survey of the most luminous sources in the nearby universe. So if you look at the X-ray luminosity versus the redshift, you can see that blue region is what I'm suggesting to look at. And the reason we really care about focusing on these sources, and I should say the purple data points that you're seeing in that region are from the BASS survey, so it surveys the whole sky. So AXIS will be looking at a small field, Cosmos or some other type of field that's a very small region of the sky, so you would have low luminosity sources at low redshift. But if we want to find luminosity analogs, we really have to survey the more luminous systems. And so these are some of the sources, and you can, just looking at the images, this is SDSS quality images. You can see some of these have multiple nuclei. None of these have been looked at with Chandra, and actually if you wanted to get decent sensitivities with Chandra to a decent level of obscuration, you would have very long exposure times. And so the idea is basically to do a volume limited survey of all major mergers that we know from all of these sky surveys that have these luminous AGN above 10 to the 43 at redshift less than 0.1. So we can do this with AXIS, looking at the 488 sources that have never been observed with Chandra in about a megasecond, and then we'll get 10 counts even for companions that are at Compton thick levels with 10% of the flux. So it really allows you to get these very obscured systems, and we can go down to 1 kiloparsec just because these systems are very nearby, so we get very high physical resolutions. So just to show you why luminosity matters, so this is bolometric luminosity versus fraction of mergers. So you really do have to have luminosity analogs just because you have such a higher fraction of mergers at high AGN luminosities. And on the right is showing you what AXIS does. So it gets very many systems once you get to redshift 0.2 or 0.3 when you're above 10 to the 42. But because it's a small sky area that you're going very deep, you really need to use the full sky to get these luminosity analogs. And this is just showing what Chandra can do and why it matters. So this is different curves for on obscured AGN at different luminosities, 42.4, 42.8, 43.5, and then the red is showing you what you would get for a mildly Compton thick source of 10 to the 24. And so you can see then there's dashed lines for the number of counts, 3 or 30. But the Compton thick AGN are basically, even with 100 kiloseconds at 10 to the 42.4, that dashed lines are basically undetectable above redshift 0.1. So you really do need these much deeper exposures that AXIS will give you. So just an individual example of how complex this can be. On the left is showing a near-infrared image of a source that has these dual nuclei separated by kiloparsec separations. The middle, so in the near-infrared it's very clear, but in the middle I'm showing in the heat map is HST. You have this huge dust lane across the secondary nucleus. So we actually got HST spectroscopy before we got the image, and you don't see anything because you have this big dust lane that covers the blue band. There's actually 3 nuclei. When you look at it in the radio, there's 3 nuclei. So we think the third one is probably just star formation. But the X-rays really can cleanly separate this out. But showing on the right is what this is separated by 2 arc seconds, so it's something AXIS can do very well. But with Chandra, even with 25 kiloseconds, there's some photons there at hard X-rays, but you don't have enough to do spectral modeling to really understand, is this a luminous Compton thick AGN? And because the other source is fairly bright, it's very hard to separate this out. So this is something that AXIS will really help with to get a lot of photons and figure it out. So why does this matter? So as I mentioned in the beginning, this really is a full story. And so if you want to understand, how many binary AGN are, or what is the gravitational wave signature, you really have to constrain dynamical friction. So you have to understand how fast galaxies merge. And this is something where mergers and dual AGN, where we know there's a black hole there, are really critical to get an idea of what the number densities of these systems are, possibly what the fraction of binary AGN are. So this is why this is so critical to have very high spatial resolutions that you get in the low redshift universe. Low redshift universe, we can also get very good measurements of the black hole masses. So this is important because then we'll have good predictions about what the signal might be, whether LISA or the pulsar timing rays might be sensitive. This shading map is showing you sort of where LISA and the PTAs what their sensitivity will be now and sort of in the future. And on the right is showing you basically velocity dispersion measurements from a 230 parsec separation dual AGN that we recently discovered. And you can actually measure black hole masses from velocity dispersions for these systems. So it gives you a really interesting insight into the types of signals you might have. So just to give you a quick summary, so AXIS will detect 20,000 AGN in its deep and wide surveys, and it will really enable the first study of dual AGN activity for a large, complete sample across redshift. I think a geo survey of all nearby luminous AGN that are in major mergers will be a critical step to make a comparison to that great survey of distant dual AGN, because we can reach kiloparsec separations and very obscured AGN. And there's just so many strong opportunities for multi-wavelength follow-up in terms of understanding how we can detect these AGN, because when you combine the X-rays, with the near-infrared, mid-infrared, with ALMA, you can get much tighter constraints on whether you actually have a highly obscured AGN there. And another critical point is that dual AGN really allow us to bridge the gap between binary AGN and gravitational wave detection. So they're very critical to understand. So thank you so much.
Questions?
Very exciting, Mike. I was just curious, for the candidates that you currently have, do you have a separation distribution? I know the selection was less than 10 kpc.
Yeah.
Do you have a plot of that? I'd be very curious to see. Obviously, I know that there are observational
I
constraints on that
didn't put the
included.
separation
Okay.
distribution, but it's actually really interesting. I didn't talk about this in this particular, but actually for the obscured sources, they peak at smaller separations, which you would expect from simulations. And actually we found a lot of these, actually that 230 parsec separation one is a luminous obscured AGN. We looked at it with AO thinking maybe the simulations are right, and we found a lot of these. So I think there's still a lot of, hidden populations that we can find from nearby systems. So.
Wait, any other questions, Richard?
Is the Euclid near IR sensitivity and angular resolution sufficient to follow up to find things for you without doing brute force AO?
It's a lot better. Roman will be way better. It won't survey the same fraction of the sky, but the issue is the Euclid detector. When you go into the near infrared, the pixel sampling is much worse. Obviously, the PSF was worse too, but it'll still be way better than all of our existing surveys. But I can't remember, is Euclid actually surveying the near infrared as well as the visible? Yeah. Gets them both at once. Yeah.
But in any case, sorry, I don't want to jump into my talk, but the problem is, you might see 2 point sources with Euclid. Now, whether you have 2 AGNs, that requires.
Yeah, you have to have the X-rays. Yeah. Right. Great. Yeah. I think this is why by the 2030s we'll have incredible imaging for all of these nearby systems from Euclid and from Roman.
Okay, well, with that segue into the next talk, we can thank Mike again. I think you just want to stand in front of this. Yeah, that was.
Okay, start presenter tools, right?
Yeah, I think they should show up.
So she opened the PowerPoint.
The bottom one there, very bottom, yeah.
Excellent.
Okay, so our last talk of the session is Ezekiel Treister. Treister. All right, thanks.
Okay, well, thank you very much. Thank you for the invitation to present this work today. I'm very excited about the opportunities that Axis will open, in particular to search for dual AGN and to expand our knowledge of dual AGN. Now, it's very timely that I talk about it after Mike. I think you save a few minutes on the introduction. Also, we've been working together on this topic with Mike for several years. And actually, this is, I think, a good example of the synergies that can be established. Is there a problem? Oh, sorry.
screen.
Yes.
For desktop.
This one?
Yeah.
No, the top
Oh,
one.
full, yeah, okay.
Because
Yeah, then you'll see presenter tools.
Is that better, Chris?
Yeah, and if you
Now you
just
can go back into.
okay, is that okay? Excellent. Okay, sorry. Anyway, you didn't miss anything if you were watching online. I was just introducing the talk and saying how this is a very good example of the kind of synergies that can be established with AXIS and other observatories that are either working now already or that they will be available at the same time as AXIS, hopefully. Now, okay, there you go. Now, I don't think I need to work very hard to convince you that establishing an observational connection between black hole growth and galaxy merger is important, but it has been, at least on the observational side, very challenging. Identifying mergers is very complicated. It's something that is still debated heavily. Identifying AGN in those mergers has been very difficult, and even more importantly, identifying an observation and a convincing connection between the galaxy merger and the AGN or the black hole growth event has been extremely challenging up to date. Now, on the observational point of view, it's been very challenging because there are many biases, many selection effects that need to be overcome in order to address this problem. Now, of course, Mike already mentioned that, and hopefully I don't need to convince you too much about the importance of, in particular, the dual AGN phase. At least from simulations, we know that when the two black holes are closer to each other, that's when you expect most of the black hole growth, and also a peak in the obscuration of the system, which again tells you why it has been so difficult to identify and study these sources. Now, at least in the local universe, we have a few confirmed systems. We have been working hard in expanding this sample, but again, it's a very difficult and challenging task. We have samples of very few sources of confirmed dual AGNs. They have separations ranging from about 1 to about 10 kiloparsecs or so. But again, this is an area where the multi-wavelength approach and combining observations with, for example, ALMA, with the confirmations that AXIS can provide is very important, and I think we can make a significant progress of that. So the main topic of this talk and what I want to present today is how we can use ALMA to identify very, very strong, very confident candidates for dual AGN systems that then we can confirm with AXIS. And the way to do that is through the sort of millimeter emission, continuum emission from AGNs that is detectable with ALMA. Now, here I'm not talking about radio loud AGNs. Of course, we know radio loud AGNs are very strong emitters at these wavelengths, but what we've been discovering the last few years is that also radio quiet AGN emit at sort of 100 gigahertz or so emission. And this emission, we think, is coming from very, very close to the black hole, from the coronal emission, and it's likely originated by the self-absorbed synchrotron emission from a very compact, again, very few RGs nuclear region, and that is, in principle, directly connected to the black hole accretion. Now, this has been in the last few years, and the BUZZ survey has been described before, but thanks to the BUZZ survey and the study by Taiki Kawamura and Claudio Ricci, there has been a very established, very significant correlation between the sub-millimeter continuum emission and the X-ray luminosity. the most likely explanation is that they're both directly connected to the black hole accretion rate, and therefore that's why you expect a very strong, the strong correlation that we see. Now, what is interesting, but is very useful about this is that on the one hand, the sub-millimeter continuum emission is not affected by obscuration, so it allows us to trace even heavily obscure systems. But also, thanks to ARM observations, now we can reach spatial resolutions of something like about 0.1 arc seconds or so. So we are able to identify dual AGN systems using the sub-millimeter continuum with ARM observations. Now, establishing the feasibilities of these studies and actually observing the sub-millimeter properties of dual AGN is the main goal of the thesis of the PhD thesis of Macarena Droguet, working with me at Universidad Católica. And the first question that she's trying to answer is whether these dual AGN are found in the same correlation, because this correlation, which was mostly obtained for bus sample, for bus sources, is mostly for isolated systems. Now, of course, as you may expect, the dual AGN, the non-dual AGN, appear to follow the same correlation, taking into account the scatter of the correlation, but as expected, they seem to follow the same correlation. Now, what she also did is that she incorporated mergers, galaxy mergers in the local universe selected for the infrared emission. So these are mostly Eulers, in order to see whether they follow this correlation as well or not. And what you find is that most of the Eulers in the nearby universe from the gold sample are significantly away from the AGN correlation. And you might expect, and you might interpret this, because most of the both the millimeter and the X-ray emission in these systems appear to be dominated by star formation processes and the dust in the nuclear regions of this system. Now, what is interesting is that there are several sources in this very small sample of about 20 Eulers in the local universe, in which they seem to be found in between the correlation that you expect both for AGN, which actually I will use a pointer, that this is the so-called Kawamura relation for the AGN system, and this is for pure star-forming galaxies or galaxy mergers. And several of these systems seem to be found in between these two, which indicate the presence of AGN, and in particular the potential presence of dual AGN. Now, in order to test for that, we also obtained ALMA time in the last 3 or 4 years in order to follow up these sources using the sub-millimeter continuum as a proxy for dual AGN. We have in total about 35 hours of high-resolution observations with the 12-meter array to go for the very small nuclear separations, less than 1 kiloparsec, and about 60 hours with the ACA, which is the more compact array for the wider separations reaching up to about 30 kiloparsecs. And just talking about the continuum results, we have a sample of candidates, of dual AGN candidates now that we identified with the ALMA emission at sort of less than 1 or about 1 kiloparsecs or less separation, including one that, if it's confirmed, it will be the record breaking at 120 parsecs. We also have much larger samples of wider separation systems between 10 and 30 kiloparsecs. These are only results from our cycle 10 data. We also have cycle 11 data from AMA, sort of doubling this sample, and we propose for further cycle 12 observations. Now, what I'm going to claim is that these are in the very interesting targets to follow up with AXIS, because as I say, I was mostly talking about candidates, because confirming that they actually hold and that this emission is due to two AGNs has been, it requires X-ray observations like the one that AXIS can provide. AXIS, as we all know very well, has both a very high spatial resolution and at the same time is very sensitive, and combining these two makes it the ideal tool to confirm the dual AGN candidates in these systems. Now, considering the sort of 1.5 up-second spatial resolution of AXIS, we should be able to resolve nuclear separations of up to about 10 kiloparsecs in up to redshift of like 0.6. So basically for this regime, we will be able to obtain it still in the relatively nearby universe, but much further away that we have been doing it so far. We should be able to identify both a luminous X-ray emission and study the iron K alpha line to confirm the nature, to confirm the presence of dual AGN in these systems. Now, because of the sensitivity and the field of the area, sorry, the effective area of AXIS, we should be able to detect and confirm this dual AGN in only a 10 kiloseconds or a few tenths of kiloseconds observations with AXIS. And that opens, just to conclude, basically it opens this new window to obtain large significant samples of dual AGN, which we haven't been able to do so far, and basically in combination with future observations. And basically the way I'm proposing we can do that is we can start from morphologically selected samples, mostly obtained from imaging obtained with Euclid and Rubin. So we pre-select for example, post-merger or late-stage merger systems. Then we follow up with ALMA in order to obtain dual AGN candidates from the system based on the millimeter continuum emission. And then finally, we confirm their presence with AXIS in a few kiloseconds observation. So hopefully in the next decade, we will have significant, statistically significant and more complete samples to answer some of the key questions. Some of them has been already raised so far. So thank you very much.
Thanks. So on your plot with the ULERGs on the millimeter to X-ray correlation, I thought you were going to say that the X-rays are being obscured and the millimeter can penetrate. But then you said, oh, this is actually, we think, star formation, if I understand correctly. Yeah, why is that? Are we actually,
Okay,
is that picture plausible?
Sorry, yeah, no, that's an excellent point. Let me go back to that, and thanks for the opportunity to maybe go into a little bit more deeper. We think that's absolutely true. What we think it's happening is that the reason why they are in between the correlation is because the X-ray are obscured, but the millimeters are not. But you still have a combination of both nuclear star formation and in AGN as well. And really, the only way to tell them apart is to place them in this correlation and see where they fall. And basically, while there's a mix, and we cannot entirely rule out that some of these sources have a hidden AGN, it's just that they won't contribute much. But most of these sources in between are actually a combination of a star formation and heavily obscure AGN as well, which we start to see in the millimeter, but also that they are obscuring the X-rays.
Got it. Thanks for clarifying.
Yeah, so I'm interested in these dual AGN, and really this is a question that is as much for Suvi as it is for you. But when you put together this list, how much of this is going to be informed by what Rubin finds? And in particular, I'm really interested in this off-center TDE that was found, and you know, it's fascinating, and you know, there's going to be a lot more of these, and so these are going to be really important to really figure out the activity of these roving black holes, if you will.
Yeah, absolutely. And I absolutely agree. And in fact, it's sort of a follow-up of Richard's question at the end of Mike's talk. We should start, I mean, Rubin and the combination really of Rubin and Euclid is fundamental to sort of to create the parent sample, I think. We need to start from a population of galaxy merger candidates. We start with galaxy mergers, which I guess they will have to be selected from their morphology. We will need to look for evidence of tidal tails, of strong distortions, and that's an entire talk on its own. It's very difficult. We will have to rely on AI machine learning techniques just to obtain it, and we've been working on that as well. But then identifying the galaxy mergers is only the first part. Then we need to find the AGN in those, whether they are AGNs on those. And that's where the combination of ALMA first and AXIS later, I think it will be critical. So this is really a multi-wavelength effort, and I think it's the only way to do it. But luckily, we should be able to do it in the next few years.
Yeah, I have to agree, but I one thing I do want to caution, that one TDE that I mentioned does not look like the host galaxy is terribly disturbed.
Yeah, no, and it's not going to be easy. I'm not going to claim that it's going to be easy or that we are going to be complete. Yeah. So.
Okay, so with that, let's thank Ezekiel and all the morning